Good morning, everybody. Thanks for coming to class. Today we're going to start lesson 2.4, which is on complex numbers. And to begin with, we're going to talk about the imaginary unit, I. So the imaginary unit I is equal to the square root of -1. You guys first learned about this in Algebra 2. And with that understanding, you should remember and know that I squared is equivalent to -1. That's going to be important for simplification purposes. So we're going to use that with complex numbers. Now, a complex number is a number that can be written in the form a plus bi. So a complex number has two parts to it. It's got the real number part, the a, and it's got the complex number part, the b, that has an imaginary unit attached to it with an I. So that's what a complex number is. So you're going to have a few different types of problems. The first one is very simple. We have to express in the form a plus bi, a complex number, where a and b are real numbers. So here they're just giving us two different complex numbers, and we just have to add them together. Well, that's just combining like terms. So the 3 plus the 2 would give us a 5. The 4i plus the 5i would give us a 9i. Really simple problem. We had two complex numbers. We added them together to get a new complex number. Part B is similar, except for instead of adding the two complex numbers, we're going to multiply. Well, when you multiply two complex numbers, you need to use the FOIL method. So 3 times 2, 3 times 5i, 4i times 2, and then 4i times 5i gives us 20i squared. Now this can be simplified. Obviously the 15i and the 8i give you a 23i, but that 20i squared changes into -20 because I squared is equal to -1. And then of course we still have the 6 in the front, and now we can combine the 6 and the -20 to get our answer of -14 plus 23i. So as you can see, we used the understanding of I squared equals -1 to help us simplify that expression. The next problem is a little bit tricky. It's pretty straightforward, but it gives a lot of students problems. It says find the values for x and y, where x and y are real numbers. What we're going to have to do is set the real number part, 2x minus 4, on the left side equal to the real number part on the right side. And then we'll have to set the imaginary number part on the left side equal to the imaginary number part on the right side. So now in doing this, we can obviously solve for x over here. X equals 6. And over here on the right-hand side, we can divide both sides by 3i. And in doing so, we get 3 equals y. So we just solve for x and y. The next example is very similar to some of the problems we were doing before. Part A gives us just a little bit more steps, but we're going to have to distribute that 4 to get 8 plus 20i. And then we're going to be subtracting this other complex number. And so now we do this by taking 8 minus 3, which gives us a 5. The 20i minus a -4i really becomes a double negative, so 20i plus 4i gives us 24i. And that's the result you'd get by subtracting those two complex numbers. Part B, again, this is multiplication, so we'd have to use the FOIL system. So we get 8 plus 4i minus 6i minus 3i squared. Simplifying would give us 8 minus 2i plus 3, and so we get 11 minus 2i as a result. Part C, we'd have to take the 3 minus 2i and FOIL it with itself. We still have this I in the front. So that's going to give us 9 minus 12i plus 4i squared. And that would simplify into 5 minus 12i. Then we distribute the I, and we get 5I minus 12I squared, and then that would simplify into 12 plus 5I. Then, for the next two problems, we have imaginary units with large exponents. So before I get to that, let me just talk about how imaginary units cycle. So we've already talked about how I equals the square root of negative 1. I squared equals negative 1. I to the third would equal negative I, and I to the fourth equals positive 1. Well, after that, it continues to cycle. So I to the fifth is the same thing as I to the first. I to the sixth is the same thing as I to the second. I to the seventh, same thing as I to the third. I to the eighth, same thing as I to the fourth. And again, it continues to cycle. I to the ninth is the same thing as I to the first. I to the 10th, same thing as I to the second. I to the 11th, same thing as I to the third. And I to the, let's fix that. I to the 12th, same thing as I to the fourth. And it keeps cycling every 4 units. So with that being said, when we have to do a problem like part D, simplify I to the 51st power, what I'm going to do is I'm going to rewrite this as I to the 48th times I to the third, because properties of exponents say we can add the 48 and the 3 to get the 51. Now, why did I break it apart into a 48 and a 3? Because I to the 48th is the same thing as I to the fourth raised to the 12th. And why did I break apart that 48 into a 4 raised to the 12th? Because I to the fourth is just equal to 1. And now 1 to the 12th is just equal to 1. And if you remember on the previous page, I had I to the third equal to negative I. And so this whole expression just simplifies into negative I. The last problem here, we have a negative exponent. So I to the negative 13th. What I'm going to do here is I'm going to break that apart into an I to the negative 16th times I to the third, because properties of exponents say we can add those two exponents and that would give us the negative 13. Well, the reason why I do this is because that I to the negative 16 is the same thing as I to the fourth to the negative 4. Still got the I to the third. And now I to the fourth is equal to 1 to the negative 4. Again, I to the third is equal to negative I. And so this whole expression simplifies into negative I. It's just really exciting stuff, isn't it? You guys love this. Okay, so last thing I want to talk about is conjugates. You guys have heard me use this word lots of times before. But a conjugate related to complex numbers, you can see if we've got 5 plus 7i, then its conjugate would be 5 minus 7i. So the first term is always the same. It's the second term that is the opposite. So you can see some additional examples here. 5 minus 7i, its conjugate would be 5 plus 7i. The conjugate of 4i would just be negative 4i. And the conjugate of 3 is 3, because you got to think of 3 as 3 plus 0i, and so its conjugate would be 3 minus 0i, and both of those expressions are equal to 3. So why I talk about this is because we're going to discuss taking a fraction that has imaginary units in the bottom and simplifying. So just like we have a rule where you can't leave square roots in the bottom of a fraction, we've got a rule that says you can't leave imaginary units in the bottom of a fraction. So what you do is rationalize that imaginary unit, and to do that, we multiply the top and the bottom by the conjugate of the denominator. That's what I call the ancient Chinese secret. So now I have to FOIL out the bottom, and when I do that, I get 81 minus 18i plus 18i, and then minus 4i squared. Top obviously just stays as 9 minus 2i. Now, did you notice on the bottom when I FOIL conjugates, the middle two terms cancel? So that results in, again, we still have 9 minus 2i on top. The bottom becomes 81 plus 4 because that I squared is equal to -1. So my final answer is 9 minus 2I divided by 85. So that's simplifying or rationalizing a complex number from the denominator. So next, we're going to FOIL out two complex numbers here. Now, in case you don't remember, if we have the square root of -9, like you can see here, we can change that into a 3I. Because the square root of 9 is 3, and because there's a negative inside of the square root, it has an I attached to it. In the same way, we can change the second set to -1 plus 2I, because the square root of -4 is equivalent to 2I. Now we can FOIL just like we did on previous problems, giving us -5 plus 10I plus 3I, and then minus 6I squared. This would result in giving us, what is that, a 13I, and this would be -5 plus 6, which is a 1, and so 1 plus 13I would be our result. Tomorrow I'm going to talk about taking quadratic equations and solving those. As you guys might remember from last year, sometimes when you solve quadratic equations and use the quadratic formula, you end up with a negative inside of your square root. So that's going to be the case with some of these. Now, if you end up with a negative inside of the square root, you get an imaginary value. So we're going to talk a bit more about that tomorrow, along with a cubic equation. And so here's going to be your homework problems for Monday on lesson 2.4. And there will be a quiz tomorrow on lesson 2.3. Have a great day, everybody.